All right, so we're going to talk about the different types of bonds real quick and their general properties, and then how you can kind of recognize the difference between our different types of bonds. We already know from last term that most atoms, except for our noble gases, need either more or fewer electrons to get to their full octet, where they are happy and complete. So whether atoms are going to steal electrons, share electrons, or give up electrons to get to that full octet is going to determine how attached or attracted they are to each other. We call those attachments or attractions bonds, and that's how we end up with different molecules. Instead of everything in the natural world just being, lithium or carbon or nitrogen, the combination of those atoms are what give us our ability to have chitin and cellulose, and our ability to have things like caffeine or Tylenol. So, or something as simple as water. So our first types of bonds that we're going to look at are our ionic bonds. You guys are familiar with ionic bonds from things like table salt, right? So sodium chloride, table salt, magnesium oxide, these are all our ionic compounds. They are made up of a metal and a nonmetal. The reason for this is the difference in their electronegativities. Yeah. If we go back real quick, we can see that our metals and nonmetals, all of our metals are towards this side where we have lower electronegativities. All of our nonmetals are towards this side where they have higher electronegativities, how badly they want electrons. So when we have ionic bonds, our electrons are going to be completely transferred. So for sodium and chlorine as our examples, the sodium completely loses an electron, the chlorine completely gains an electron, they become ions. Our sodium now has a positive charge, our chlorine has a negative charge, just like magnets, they're attracted to each other. Because the difference in their charges is so high, the bond is going to be really strong. Because those bonds are really strong, those atoms are going to want to stick close together. That means that they're going to have a really high melting point because they want to be solid, they want to be close together, and they're usually going to be solids at room temperature. Most of the things that we call salts, like table salt and other salts, they're ions. That's what a salt is. So because these are made up of those ions, those charged particles, they're going to be soluble in water. So when salt pours into water, it breaks those bonds between the sodium and the chlorine, and those individual ions hang out. In addition, because those ions are charged, once they're dissolved in water, they let you run electricity through it because of the charges on those ions. Water with no ions in it actually doesn't let electricity run through it very well. The reason why water is such a hazard with electrical currents is because there are ions dissolved in it, like tap water. If you have totally pure water, it doesn't have electricity run the same way through it, as is a problem for us, like why you have to be careful with water and electricity is because of the ions and how well they transfer electricity through it. So next is our polar covalent and our non-polar covalent. I'm going to talk about polar covalent first. So when we have two nonmetals, their electronegativities are going to be closer, so they're both going to want the electron. One of them isn't going to be willing to give it up completely. However, with polar, that means that the electrons are shared unequally, which is going to create a partial charge. So here is our example. We have hydrogen and oxygen. Our oxygen is going to end up with a partial negative charge because it wants the electrons more than the hydrogens. So while they're sharing them, the oxygen holds on to it more. So like if you're really hungry and your friend's kind of hungry and you split a meal, right? The one who's really hungry is going to end up with more of the meal. That would be oxygen in this case. So it's going to end up with like a partial negative charge, while our hydrogens are going to end up partially positive. Not as much as the ionic compounds, but still there is a little bit of like how a magnet has a positive side and a negative side, there's a little bit of that going on. The unequal sharing of electrons means that their bond strength is moderate to high. Usually not as high as most ionic compounds, but still pretty strong. It's not easy to split a water molecule apart. So the polar covalent molecules, because they have a moderate strength, they can be solids, liquids, or gases at room temperature. It really depends on how polar they are. So our two examples that we show over here are water, which is a really important polar molecule. And then this is hydrofluoric acid, where we have a positive on this side and a negative on this side, where like a magnet, there's a positive and a negative side. Because there's a partial charge to it, and because water has a partial charge, these molecules will be soluble in water and other polar solvents or polar liquids. And because of the partial charge, they sometimes will conduct electricity, sometimes not. Polar covalent is somewhere between covalent and ionic. There's some charges happening, the electrons aren't shared equally, right? It's not fully polar because it's not fully ionic because we didn't steal an electron, but there are some things that are going to be similar, like our moderate to high bond strengths, the fact that sometimes we'll conduct electricity, and the fact that we're soluble in water are similar to our ionic compounds. Then we have non-polar covalent. So non-polar means that there is no side. So just like we have north and south on the north and south poles, or the north and south poles on a magnet, these do not have poles. There is no side that is positive, no side that's negative. They're totally non-charged and equal. These would be a nonmetal and a nonmetal that are super similar in electronegativity or are the same element, so they have the same electronegativity. So if I have two hydrogens that are bonded to each other, like here, both of these hydrogens want these electrons the same amount, so they're going to share them equally. So there isn't a positive side, there isn't a negative side, there is no charge. Because they're sharing the electrons equally, the bond strength is relatively weak. Because the bond strength is relatively weak, they don't need to be super close to each other. They're going to have a really low melting point. If the atoms don't need to be close to each other, they can spread out more easily, which means that at room temperature, a lot of these are going to be liquid or gases. Of course, there are always exceptions, we know that, right? But for a lot of these, they're going to be liquid or gases at room temperature because their atoms don't need to be so close together. The examples that they give here are methane, which has hydrogens and carbons. These are all nonmetals, and because the hydrogens are spread around equally around the carbon, they end up evening out any charges. There's no positive or negative side on these. And then the other one is our atmospheric oxygen. Because there's no charge, they're not going to be soluble in water. You guys can probably think of some really obvious examples of something that must be non-polar because it does not mix with water. So things like oil, right? If you mix oil and water, they don't combine, they don't dissolve. They will split back out because one is polar and one is nonpolar, and polar and nonpolar things don't mix. Because there's no charge, these molecules also will not conduct electricity. There's no way for the electricity to move through it because there's no charges. Okay, the last two are network covalent and then metallic bonds. Network covalent is when we have nonmetals and nonmetals that form these crazy grid patterns that are super strong. So one of the really common examples of this is diamonds are a really common example of this guy. Because of the lattice structure of all the carbon molecules, diamonds are super, super strong. Their bond strength isn't about a single bond. It's not about one of these. It's about all of them together. So their network is going to make their bond strength really, really high. The molecule's strong bonds means that they're going to have a high melting point and usually be solid because the bond is strong and they want to be close together. It's hard to turn them into a liquid. It's going to take a lot of energy for those bonds to start to get less intact, right? So 2 examples that they give are diamonds and quartz. Usually they're not going to be soluble in water or any other polar solvents. Like if you drop a diamond in water, it's not going to disappear. And the lack of charge usually means it's not conductive if it manages to dissolve in water. Some of them can dissolve and some of them can be conductive, right? Because this is a really broad subject of things. And we are learning more about these as we create more of them in the lab, but a lot of our naturally, the ones that exist naturally, like graphite and diamond, are not very conductive or they're not going to dissolve. And then our last one are metallic. So when you're dealing with metal like an aluminum can, or you're dealing with steel, it's all the same atom unless you have a alloy, right? But what you end up with is all of these atoms together, and they all share electrons. So the electrons are freely moving between all of these atoms. They're all sharing them. That's why it's so easy for electricity to run through them. So the sea of electrons holding them all together makes their bond strength really high. This is why most metals are going to be solids at room temperature. They're not soluble in water, but even if they're not dissolved in water, just solidly, most metals are going to be really good conductors of electricity because those electrons that we need for electricity can just move. They're not stuck to one atom, they just slide around.